Right, so in this video I'm going to be explaining another important article, but this time is about domain generalization. It's not about domain adaptation. It means that even we cannot use the samples, there is no target, the target is unknown. So this article in 2023. Domain generalization is about learning models that generalize well to new unknown domains that are related to but different from the training domains. It is a fundamental problem in machine learning and has attracted much attention in recent years. A large number of approaches have been proposed. Different approaches are motivated from different perspectives, making it difficult to gain an overall understanding of the area. So we propose a causal framework for domain generalization and present an understanding of common domain generalization approaches in the framework. Our work shed new light on the following question: what are the key ideas behind each domain generalization method? And why is it expected to improve generalization to new domains theoretically? How are different domain generalization methods related to each other, and what are relative advantages and limitations? By providing a unified perspective on domain generalization, we hope to help researchers better understand the underlying principles and develop more effective approaches for this critical problem in machine learning. So, deep neural network models tend to exploit spurious correlations. For example, A, snowy backgrounds are associated with wolves. Or B, rules are associated with malignant skin lesions in cancer or healthcare. This is a causal domain generalization framework. For example, in A, you see that a data generation model for a domain, and it is called the CLD, where this P star here are invariant across domains, as indicated by solid edges. So when we go to a different domain, it is invariant. It consists of a feature extractor F5. This is the feature extractor. And a linear classification head G sub W. So why are your labels? Because we are doing classification, but H here is just a vector of feature extracted from input X. So we assume that each domain distribution, in the family P, is a marginal of another distribution. So in domain generalization, we usually have multiple sources. So we say multi-source domain generalization. And it's different from multi-source domain adaptation, because in domain adaptation, your target is fixed, but in domain generalization, first of all, you don't have access to the samples of the target. Second, your target is unknown. It could be anything, so we leave it unknown. We should also guess and discover some of them. Different authors refer to the two latent variables using different terms. We decompose our feature into XC and XN. So some people say semantic and variation factors. Some people say intended factors, non-intended, domain independent and domain dependent. I usually say domain invariant and domain specific. This is what I always say. The graphical model introduced is called the style and content decomposition. And XC and XN are called content and style variable. So in this paper, they call it content because it's domain invariant, and XN is style because it depends on the style of that image, for example, background color, what kind of background color or anything. But here, instead of the I and the S, they decompose it as XC and XN. And so similar models appeared recently in a number of papers. So the variable X sub C denotes the essential information in an image that a human relies on to assign a label to the image. It is hence said to represent causal factors, intended factors, semantic factors. So as I said, the term style should be understood in a broad sense. In addition to image style, it also includes factors such as background, context, object pose, for example, rotation of that. For example, all images that have rotation of 30 degrees, for example, in MNIST dataset, consider it as domain number 3, for example. So if we introduce a similar concept for prediction, and to ground this causal latent decomposition model, we need to specify 3 distributions. Due to this causal invariant generation assumption, the last 2 distributions do not change across domains. So these 2 do not change across domains. In contrast, the first one, this one, may be different from different domains. So the 3 distributions define a joint distribution over the 4 variables. This joint distribution defines a domain, and we refer to the collection of such domains for a fixed P star family like this. In each domain, examples are generated so we draw from this distribution P. So we draw from, and X and Y are observed, while X sub N and X sub C are hidden. And we will use uppercase letters to denote variables and lowercase to denote their values. As I said, we have different kinds of domain shifts: concept shift, label shift, covariate shift. Of course, some people say conditional shift as well. Consider source domain P sub S and target domain from a CLD family. The first inequality states that different domains may have different distributions of training examples. So this is just the covariate shift. The second inequality, this one, means that the conditional distribution of y given x may change from one to another. So this is the concept shift. The concept has been shifted because, for example, pandemics has come, and now what has been considered like flu, it becomes coronavirus. So your labels are changed. Although the feature is still maybe the same or close, but the label is totally changed. And now the third one. The third one The third inequality states that correlations between y and xn may vary across domains. In this sense, those correlations are spurious. Domain generalization in the presence of both concept and covariate shift is difficult. Of course, we cannot decouple them. It's very hard to decouple these kinds of domain shifts such as concept shift, label shift, covariate shift. But in this paper, we adopt CIG assumption and they remain constant across domains. We assume that they are constant across domains. Now, besides a data generation model, our framework involves two other models, a prediction model and a fused model. A prediction model is a neural network model with parameter theta. It is trained on the source domain or multiple source domains. But the fused model is a technical model created by combining the prediction model and P star. The two dots here you see indicate the combination of the two models. The fused model enables us to characterize the dependence of prediction output on the latent factors. Shortcut learning. The cross-entropy loss of a prediction in a source domain is just expectation of minus log of that probability. It is sometimes referred to as in-distribution. We can estimate the ID loss from a training set from the source domain. This is known as empirical cross-entropy. In the data generation model, Y depends only on the core factors. In the prediction model, P hat, theta, Y hat depends on X, as X depends on both X sub n and X sub c. In the data generation model, the predicted label depends on them indirectly. So ERM is usually done using gradient descent, which tends to latch on to strong and simple correlations between X and Y. As X depends on both X sub c and X sub n, domain invariant features and domain specific, the gradient descent captures not only correlations between X sub c and Y, but also those between X sub n and Y. It does not distinguish between these two types of correlations, which leads to internalization of easy-to-learn correlation between X sub n and Y to the prediction model. This is known as shortcut learning. Shortcut learning renders the dependence of Y hat in the prediction model similar to the manner Y depends on X in the source. As the dependence is spurious and is not shared by the target domain, the quality of prediction in the target domains tends to deteriorate. A model that predicts wolves based on snowy background would misclassify a husky in the snow as a wolf, and may also misclassify wolves in other backgrounds. Similarly, a model that predicts malignant skin lesions based on the presence of rulers would do poorly on images without rulers. Suppose P hat is a prediction model trained on a source domain from CLV family. So we establish conditions for optimal generalization to target domain P in the same family. the conditions for p hat to minimize the out of distribution cross entropy L. So let x tilde be another example sample from the xc and a different x tilde. Now the two examples contain the same semantic contents and hence should be classified into same class. For example, one of them has the background snowy weather, the other one doesn't have. In this sense, x and x tilde make up a contrastive pair. I have a playlist for contrastive learning, so you can learn about it. There are very similar concepts. We say that a prediction model is causal invariant if their labels are invariant. For any x and x sample from any x sub c and x sub n. So the prediction output does not change in response to variation in non-core factors. The concept of causal invariant prediction is not a new one and frequently appears in domain generalization literature in various forms. It is closely related to a notion that has a very similar name, invariant causal prediction. One difference between the two is that we are concerned with the invariance of prediction with respect to a latent variable, which is entangled with another latent variable to yield the observed output. Our objective is to make the prediction model invariant to x sub n, although we cannot observe it. So let p hat be a prediction model, p be a fuse model. So if p hat is causal invariant, then conditioning on xc and xn should be same as conditioning on xc and x tilde. In a prediction model is causal invariant if and only if it is causal faithful. So this is an illustration of concepts and results. A prediction model is causal invariant if it depends only on x sub c, but not x sub n, and hence makes the same prediction on all examples sampled from the same vertical line. And then it says let p hat be prediction model, p as the source domain. Suppose that p hat is causal invariant, p hat minimizes the in-distribution loss, then for any x, we have the probability of the label is the same if you even condition an x or condition o. So we are reducing your sample to just the x sub n part, to the invariant part. Note that the requirement is minimized means that not only the parameters of the prediction model is minimized, but it's also architecture. Contrastive pairs for domain generalization. Suppose we have a collection of contrastive pairs. To enforce condition 1 and 2, a simple and direct approach is to solve this following optimization. So if we turn the constraint to regularization term, then we can solve this optimization problem. But your regularization, this R that I said here, can be done in 3 different ways: probability matching, logit matching, feature matching. Suppose there is a collection of labeled contrastive pairs. The following regularization term can be used to encourage causal